Coming up on Cracking Quantum.
So we're all dependent on position, navigation and timing, or PNT as a lot of that community call it. All our critical national infrastructure needs synchronization for timing, electricity being transported down the national grid, for telecommunications. All the financial systems rely on synchronization and telecommunication systems for all our financial transactions. Emergency services, you name it, there are 13 critical national infrastructures dependent predominantly on timing, but some also on position and navigation.
My name's Ash Lyons. Join me as I try and figure out what quantum science is really all about. Welcome to Cracking Quantum. Where I wanted to start talking to you is you got an OBE at the start of the year.
That's right, yes.
Massive congratulations.
Thank you.
What's actually involved there in getting an OBE? How does it work? Do you just get a nomination through one day, or do you have to put a lot of work into working behind the scenes to get it?
Well, it was related to a lot of the work I've done in the quantum program, behind the scenes in government and elsewhere, but also some of the leadership I've shown, partly probably through winning the hub for quantum-enabled position, navigation and timing that started 1st of December. But two people need to nominate you, and then it goes to a committee in government who decide whether you're worthy to win an appropriate award, or gong as some people call them. So I was a bit shocked in getting a letter, a very official letter that my wife wasn't quite sure who it come from. But that basically was offering, would I accept an OBE? And I said yes.
Is that the first you hear about it? It's just a letter through the post?
That was the first you hear about it.
Oh, wow.
And this was about 3 weeks before it was announced in the public domain. I got that letter.
That must definitely come as a bit of a shock.
So it was a very big surprise, a pleasant surprise.
Yeah,
but,
sure.
But a very big surprise.
So, very brief introduction. I'm here with Professor Doug Paul. Welcome to the podcast. It feels weird saying welcome when we're sat in your office a little bit, but welcome. You are one of those people that has lots of letters after your name. You're a fellow of the Royal Society of Edinburgh, a fellow of the Institute of Physics, and an OBE, like we just said. You are professor here in the School of Engineering at the University of Glasgow, and as you were just saying before, principal investigator of the UK National Hub on quantum position navigation and timing.
Quantum-enabled position navigation and timing.
That's the one. And that's one of the reasons that I wanted to speak to you today. I mentioned the quantum hubs a little bit as I've been talking to other people, but without going into a huge amount of detail. So maybe we can start broadly with what the quantum hubs are and what they're about.
So each of the quantum hubs is a collection of academics with administrative resource to be able to build a community. And the community is not just for the academic community, it's pulling in industry, it's also pulling in government stakeholders who have an interest in particular technologies. So the particular hub I run on quantum-enabled position, navigation and timing, that's really looking at quantum approaches, but also hybrid approaches for trying to build resilient position, navigation and timing systems. So we're all dependent on position, navigation and timing, or PNT as a lot of that community call it. And all our critical national infrastructure needs synchronization for timing, electricity being transported down the national grid, for telecommunications. All the financial systems rely on synchronization and telecommunication systems for all our financial transactions. Emergency services, you name it, there are 13 critical national infrastructures dependent predominantly on timing, but some also on position and navigation. So a UK government, or multiple UK government reports have spoken about the vulnerabilities, how easy it is to jam these very small signals that come from global navigation satellite systems, GNSS. GPS is probably the best one that most people know, global positioning systems. It's 10 nanowatts at the Earth's surface, so it's really easy to have much stronger signals that just jam those signals so you can't use them. And that's the threat today. Nowadays, the police typically get 2,000 reports a day of GPS jamming in the UK, predominantly from organised crime using GPS jammers to steal high-end cars, because all of them, for insurance purposes, now have GPS trackers on board. So the way to steal them is to jam the GPS so the police can't chase you.
Yep. And you've now told everybody how to steal a fancy car if they want one.
I can tell people, but it's only illegal if you do it.
Yeah, that's true. Are there certain places where that's like standing out as happening a lot within the UK, or is it something that's kind of distributed all over?
It's distributed in certain parts of the UK. There's a lot more expensive vehicles, and the other thing is that many of those vehicles within half an hour to 1 hour will be on a container ship going abroad. So, a lot of this is happening more in the southeast of England and certain parts of England where organised crime has access to be able to have cars going onto container ships, predominantly going to the Far East and particularly China at the moment, partly because of embargoes on certain vehicles going into China at present.
So it's that they can't get these fancy cars any other way, they've got to steal them from us?
They can't get some of them, or they can't get enough volume for other ones, but also it's a way to get a far cheaper high-end vehicle of a particular variety.
Yeah, of course. Just going back to that number, 2,000 a day, it's astronomical. And it really presents a clear picture of why we really need to take care of the global navigation systems. Why do we need quantum-enabled solutions for these?
Well, it really comes down to accuracy. So, an example in your mobile phone, if you don't get the satellite signals to give you accurate position, after only 10 seconds, using the inertial navigation system, the accelerometers and the gyroscope that's in there.
So in other words, like keeping track of where your phone has moved and how it's moved.
Keeping track of where your phone is, just by leaving it in a desktop and waiting 10 seconds, the MEMS inertial navigation system with those silicon accelerometers and gyroscopes will have a positional uncertainty of 8 meters. So after 1 hour, that's 46 kilometers of uncertainty because the error keeps on integrating up. You have to add all the errors together as you run the system. And that's really bad, as you can imagine. So that's why everybody wants satellites and triangulation from satellites, because you can get positional accuracy better than a meter in good environments.
Yeah, and you mentioned very briefly before how weak the signals coming from the satellites are. You said nanowatts, so that's a thousandth of a millionth of a watt. It's absolutely tiny. And I know a lot of the issues that we're having with global navigation systems are due to how easy it is to jam those signals. I wonder if you could maybe say a few words about that.
Yes, well, most of the jamming in the world is going on around war zones. So Ukraine, but also parts of Russia. You've also got around Gaza and most of the Middle East at the moment, with everything that's been happening this weekend with missiles going in different parts. But if I give an example with civilian airliners around Europe, last year in a 6-month period, there were 46,000 civilian aircraft recorded or reported having GPS jamming issues around Europe, predominantly relating around Ukraine and certain parts of Russia.
Yeah, I mean, there's a definite trend in the places that you laid out there. It's very definitely the war zones that we have right now.
Correct.
And just in case it takes a while for this podcast to come out, we're now at the end of June 2025. So things are really starting around Israel and Iran just now. So coming back to the quantum hubs, so we have the quantum-enabled position, navigation, and timing. There are 4 other hubs just now. Can we go through the areas that these are focused on?
So there's a quantum computing hub. There is an integrated quantum network hub. So that's communications and using networks that you may link quantum systems together, or distributed sensing and other applications that you can get advantage by lower phase noise when you use quantum resources to share information. There's also quantum sensing and timing hub.
Yep.
And the final one is the QBiomed, so quantum biomedical hub, which is completely new in the space. In the previous 10 years of quantum hubs, we haven't had anything solely just in biomedical and healthcare.
I think that each of those areas of the hubs really shows where the UK priorities are just now within quantum. Maybe actually you can say a few words about, broadly speaking, what the the UK is really good at within that quantum space and what it's aiming for?
So, the UK's been one of the world leaders with a lot of the technology, from the research side and the publications going out. I mean, other countries now have larger volumes, but if you look at high impact publications per head of population, the UK is always in the top one or two countries globally in that sphere. I think, with Peter Knight proposing and leading this whole quantum technology field, and the UK being the first to get into this area, first hubs were funded in 2014. Many other countries have copied that model, and it's not just doing academic research. A lot of the money in the UK, particularly over the last 5 years, much more of it has gone into industry to translate the technology and the research into components and ultimately into practical systems that can be on the marketplace. And in fact, if we look at the private investment that's gone in the UK, on top of the government funding, it's now £980 million, on top of government funding of, I think it's about £325 million. So that's basically more than 3 times private investment going in on top of the public investment in this space.
Yeah. And
that's unheard of in any other technology sector in the UK. Batteries, there was more government money than industry money. You look at pharmaceutical industry, again, a lot more government money went into their programs than the private investment. So quantum has sort of been an anomaly, which has helped more money come out of government to support quantum because it's a high growth area, one of the government key priorities at the moment, and we're starting to see products in the marketplace and quantum actually being used in a whole series of different application spaces.
So that brings me on nicely to the question I had in my head when you were just speaking there. And obviously huge amounts of investment. How much of that is going into quantum computing specifically? Because this tends to be one of the areas that is most public facing. Like a lot of the time people think of quantum technologies and they think of quantum computing.
Well, yesterday there was a big announcement of a £670 million going into quantum computing through the National Quantum Computing Centre. But most of what that centre will be doing is buying machines that then the centre can basically do independent benchmarking. So at the moment, we have every single company saying they have a better quantum computer because whatever.
Yeah.
But in reality, a lot of this is the salesman giving a pitch rather than hard data or running common algorithms and benchmarks to understand which machines are actually better than other machines, at least for specific problems, because some machines may be better at one algorithm, other machines may be better at others.
Yeah, and the reason I was thinking that is thinking of asking this question is because obviously we are not there yet with quantum computing in terms of actually being in an application space and producing something. But there are plenty of quantum technologies that are there. Are there any in particular within the position, navigation, and timing area that stand out as giving like real practical benefit just now and being used in industry?
Well, atomic clocks were really invented in the 1950s. Commercial ones appeared in the 1960s, and you've been able to use those in a whole bunch of areas. They're typically used for resilience in many of the networks that we spoke about earlier with critical national infrastructure. But they're $140,000 if you can buy one.
Yeah.
And not many people can afford to put that in every single critical national infrastructure node in the UK, because there's over 270,000 of those nodes in the UK.
Yep, and that's going to add up pretty quickly.
So that actually is £46 billion if you wanted to put one of those clocks in everywhere. And the consumer would have to pay that, so the market wouldn't hold up.
Yeah.
So what we're actually looking at, and one of the things that's starting to come through with first products in the marketplace now, is some of the new optical atomic clocks. And these are brand new through the quantum programs running over the last 10 years. They basically allow you to make lower size, weight, power, and cost, high accuracy clocks. So we're now starting to see a 3U rack mount clock, which is the same as the the 5071As that are $140,000 at the moment,
Mm.
with about an order of magnitude higher performance, which is getting to the sort of the primary standards and the active hydrogen maser performance, but in something that is half the price and a fraction of the size, weight, and power.
Yeah.
And that's the big opportunity of new clocks that are more accurate, that are cheaper, smaller, and we can start to deploy them more widely to bring resilience because of all the issues we've been speaking about.
Are there any other technologies that you want to discuss as being part of the hub there?
Well, the other one we're working on, and some of this is actually in every mobile phone, but there is a CMOS single photon avalanche detector array in every single mobile phone that does the facial recognition. It also turns your display off because it does range finding. When you put your display up to your ear, the rangefinder will tell you it's close to an ear, so it will switch the display off to save power.
Yes.
That actually, all the SPADs were designed by Robert Henderson at the University of Edinburgh, who's one of the co-investigators in the hub. But we've also got University of Cambridge doing InGas that gets out to shortwave infrared, and ourselves in Glasgow doing germanium and silicon single photon avalanche detectors.
Mm-hmm.
Both those two latter technologies are less mature, but they allow you to see through obscurance. So particularly if you want to see through fog, rain, mist, or
Yep.
sandstorms, so for connecting on autonomous vehicles and LiDAR systems, single photon LiDAR systems are showing far better performance at eye-safe powers over much longer distances than the visible and the CMOS-based systems can do at present. So, for a car to do 70 miles an hour, an autonomous vehicle to do 70 miles an hour, you need to be looking 330 meters ahead.
Yeah, it's a long way.
Which comes into the braking distance that you can do at 70 miles an hour. The Waymo vehicles that have LiDAR systems on that run autonomously in San Francisco, I've been in one, they're really impressive. Terrifying the first time you're in there.
I bet they are.
But they only see about 50 meters at any time.
Oh, really?
And they only run in cities at limited speeds because of that 50 meters visibility.
Mm-hmm.
But it's impressive technology because they can identify people, children, people on bicycles, motorcycles, other cars. They struggle with traffic cones for whatever reason.
So to recap a bit of what you were saying, these single photon detectors that we can use for LiDAR, the technology has become advanced to the point where in mobile phones, but for essentially visible wavelengths of light. And these are the kind of devices that have been developed by Professor Henderson in Edinburgh.
Right.
Where you're trying to take it now, as in not just you, but other researchers within the Quantum Hub, is towards those near infrared wavelengths where you can use a bit more power and you can see through fog and you've got all these additional benefits.
Well, the problem is the present commercial systems and the military rangefinders that have been used for centuries have very high powers. So the average CW power is 100 kilowatts.
Oh, wow.
Now, it's only one pulse over a nanosecond, but you have 3 10 to the 16 photons. So you really light things up when you broadcast that. The new systems run with 10 milliwatts CW. So you can see how much the power has come down, yet you can actually see almost the same distance.
Yeah.
So, on a reasonable day, you can see about 10 kilometers and do range finding over 10 kilometers at video rate. And even with 1 or 2 photons coming back, you can actually still do target recognition and build up a complete image. So that's really quite exciting for things like autonomous vehicles. But even just safety systems in every car, that's probably the first application from this technology when it comes through.
Yeah, and I can see that the range of applications that you can have in this kind of space is really probably going to be quite broad. I mean, you mentioned the sensor even that turns off the screen for your mobile phone when you put it to your face. There must be loads of these like basic gesture recognition tests that you can do with these kind of devices.
Well, we know that ST Micro Electronics, who have a base over in Edinburgh and responsible for those CMOS single photon avalanche detectors, they have a mock vehicle to have hand recognition being detected with the single photon avalanche detectors, so that you don't have to touch switches. You can just put your hand in different places to control things inside a vehicle. Now, you maybe don't want to take away the steering wheel, But you can understand if switching on indicators or switching on windscreen wipers or lights or something like that, rather than having to find a particular switch, which we all know can be difficult in certain cars, particularly if it's a car you don't know, they're looking at ways that you can use hand gestures to actually do certain functionality to make it safer and easier to use different vehicles.
This is kind of a ridiculous example, but I remember when I bought my current car, driving it back home, and it was into the evening, so it was starting to get dark, and I suddenly realized when I was in the middle of the city in a lot of traffic, I don't know where the headlight switch is, and having to like rush around and find it so that I wasn't going to cause an accident. So at least I can appreciate the need for something like that.
So I think a lot of the hubs, they're working with end users and they're working with companies to understand what new applications there might be. We're doing a lot of field trials, which is really important to de-risk the technologies, demonstrate they work in real environments, and that de-risks it for companies to actually take things to market. You want to know your technology is going to work in real environments before typically you'll get good investors coming in and large amounts of money to take the technology to market. So that's been one of the great successes of the hub programs over the last 10 years, taking things out and doing field trials, because you always find out things you never thought you would find out. My best example of this is with the MEMS gravimeter we had. And we took it out to Kelvin Grove Park and did gravity measurements across one of the bridges, because you measure density underneath, so the arch has air in the middle, there's more sandstone at either side, so there's very big density changes that are easy to measure.
Makes sense.
We discovered that dogs licking the sensor was the biggest source of noise, which we would have never predicted at all unless we had gone out and done it. And only then did BP tell us that they have problems of polar bears sitting at the sensors in the Arctic and camels kicking them in the Sahara. So you learn from the mistakes and the things that happen in field trials.
That is not what I was expecting you to say. That is a fantastic series of problems to have, definitely. Coming back to the quantum hubs a little bit, can you give an indication of how big these hubs are and how far wide-reaching they are across the UK?
So the Quantum Enabled Position Navigation and Timing Hub is 9 universities in 3 of the devolved nations. So we've got universities in Scotland, in Northern Ireland, and in England. And we also have the National Physical Laboratory as one of the other partners as well. But we now have over 100 companies engaged, and we have 24 government departments and agencies also engaged with the hub as well. So that has become quite significant. There are 34 investigators in the hub. 44% of our investigators are early career researchers, and 25% of our investigators are early career researchers with prestigious research fellowships. So Royal Academy of Engineering, Royal Society, UKRI, Leadership, and so on. And I've got all of those early career researchers leading work packages to let them learn how to manage and lead future quantum programs, because I'm not going to be around forever.
And coming from one of those people that you're just talking about that has one of these fellowships and starting to develop their own independent research, I can see how that would be really, really valuable. So,
we've got about 60 postdocs and students at the start working in the hub as well. So these are really, large communities that we're pulling together. We had our first community workshop in London at the Royal Society 2 weeks ago with the Royal Institute of Navigation. We had to increase the size of the room twice because we had so many people wanting to turn up. We ultimately ended up with 92 in the room, and everybody seemed to enjoy, and it was a first engagement over trying to bring different communities together and look at where quantum may have benefit and may have value in the position, navigation, and timing sphere.
Yeah, and that seems like it's one of the real powers of these quantum hubs, is it really connects those communities within the UK who are not just interested in the fundamental science of how you do the things, but really trying to connect with the people who want that infrastructure there. They have applications that they need these new kinds of sensors for.
So we have money to do at least 10 different community events So the next one we're planning is with the automotive sector, and actually being done in Birmingham, right in the centre of automotive manufacture in the UK.
Wow.
And that's really to see where in the automotive sector can quantum start to provide value and advantage.
Are there specific places? I mean, we discussed LiDAR a little bit and global navigation systems. Are there anywhere else that fits within the automotive sector?
Timing is going to become very important when you bring all the sensing information together
Mm-hmm.
to then understand if you've got 20 sensors in your vehicle looking at different things, you need to synchronize all those signals when you pull them together.
Yeah.
So timing and synchronization are ubiquitous in almost any electronic system that you're going to be doing sensing on. So that's one of the big opportunities. But again, there's probably a whole bunch of other sensors, perhaps magnetic sensors,
Mm-hmm.
Can be useful for navigation as well. We'll have to see if in road-based systems that is useful or it's not. But again, it's trying to see what sensors are available. Go and do some tests, listening from experienced people in those fields to understand which ones might have the most value.
Yep. And I'm sure you will have issues with dogs looking sensors inside cars as well.
Of course.
So you mentioned that it was 100 companies that are involved in the position navigation and timing hub. Are you getting the sense over the last 10 plus years that the quantum hubs have been running that things are starting to turn a bit more towards industry applications, or has that always been there?
It's always been there to some extent, but of course at the very start, the first companies I went and spoke to, the first comment I got was, we've got no interest in quantum computing.
Yeah.
And so one of the things I learned is, don't even mention quantum when you first start talking to companies. Talk about the technology and how it might be beneficial to their business and what they do. That might be supply chain and making components. It might be an end user. It might be the system integrator, whatever. Then bring in quantum once you've actually got them hooked that, yes, they have an interest in this technology. So that really has been the approach. And ultimately, the market doesn't care if it's a quantum sensor or a quantum clock or anything. It cares that it's a better clock or sensor than other things that are out there, and it will do what you need it to do for the applications.
Yeah, and that's a really good way of making sure that whatever we are producing as academics is really orientated towards the application that's going to have a benefit. We historically, particularly within the quantum physics space, have had a long period where we started investigating new ways of doing, let's say, sensing or whatever domain it happens to be in, just because it's quantum and it's interesting to us. So the impression that I get is over the last short while, around the last decade, we've really tried to focus down on not just producing something because it's quantum, but really producing something that's a practical benefit.
And I think it's maybe a more engineering approach now, where you talk to end users and you find out the requirements and the challenges first.
Mm-hmm.
Then you design a system trying to deliver something that solves those challenges. And I think certainly the way we put the QE-PNT hub together, it was very much coming from what system demonstrators do users need. Trying to solve particular challenges. We've got 2 in air, 2 in sea, and 2 in land-based systems. That was the easiest way to divide up. There's a lot of overlap in those systems because LiDAR is useful underwater, it's useful on land, it's useful in the air.
Mm-hmm.
But that in some of those domains, some of the technologies work better than others. And also, even if you're using the same technology, it may need to be configured or used at different wavelengths in completely different environments. So underwater LiDAR is best at 500 nanometers wavelength. Whilst if you look at imaging through rain, fog, and mist and so on, the longer the wavelengths you can go to, the better.
Mm-hmm.
Rayleigh scattering drops off as 1 over the wavelength to the power 4. So the longer in wavelength as you can go, radar, as we know, can see through clouds and rain and so on, but it's not so good at doing target recognition and identifying people or
Mm-hmm.
objects that you need to if you're in a car.
Because it doesn't have the resolution required?
It doesn't have the resolution because the wavelength is so large.
Yeah, that makes sense.
You're at centimeter wavelengths.
Yeah. Is there anything that you are particularly proud of throughout your career that have kind of like been a real highlight for you? I know this question is coming from a slightly different topic now.
I think there's two aspects to this. The first one is where you get technology in the marketplace that people can buy. Because ultimately, okay, we're an academic, but getting something out there that people will actually use gets tax revenues that pays for academia, it pays for education, it pays for hospitals, it pays for roads, and so on. But that's giving something back to society of money going back into the system. Because I've had a lot of money to do research out of UK government from taxpayers. So that's at least giving something back, of getting taxes back into the system. Mm. But the other one is where you see the new technologies or the science just inspiring people. And I've done a lot of outreach talks and been lucky enough to get pulled into that as a very early career researcher in Cambridge many years ago, being dropped in it to speak to the college on week one of a fellowship. And then 6 weeks later having to go and speak to 14 to 16-year-old school kids at a local school. And that's how you learn public speaking and talking about science and outreach, because the children take no prisoners. Politicians are easy. They'll just switch off or ignore you. But children, if you do anything that you go back in yourself or you patronize them, they will rip you to shreds.
That sounds very familiar. I know from even doing small things like tours around our lab facilities, occasionally when you have kids in, you'll get a question that just comes out of nowhere and you think, I really should know the answer to that. But it's just because I think of a different way of thinking more than anything else. We kind of get ingrained as academics into thinking about things in a certain way. So when you've got someone coming along from a completely different perspective, they tend to pop out some really interesting questions.
But that's great because it keeps you on your feet and allows you to think about analogies to explain it better the next time.
Yes, definitely.
And for teaching as well, good teaching is finding those analogies that everybody can understand, really illuminating what the equations are involved in the science, and making that come to life in ways that not everybody can look at an equation and understand what that's going to look like in real space or Fourier space or whatever.
Do you think that's a particular problem within quantum? Because it's hard to form analogies that really kind of paint the picture of what's happening with some of these fundamental quantum ideas.
I think there are some people that are very good at it. The problem with quantum is that the effects are so completely different from everyday experience because we're used to the macroscopic world. And the microscopic world of quantum gives you effects that you do not see in the macroscopic everyday life. Mm-hmm. And the problem we all have is we're just not used to seeing these effects every day. But I think, as somebody who learned quantum mechanics over 30 years ago, now you just take things for granted. You do the mathematics and this is what you get. But you can explain some of the stuff quite easily to students and to school kids, enough that they can understand what's going on without going through all the mathematics and everything else, and give them at least some idea of the physics and the science going on in the background that makes the effects happen.
It sounds a little bit odd, but I always get the feeling that we have people within our community that rely a little bit too much on the mathematics for understanding. I'm very much hands-on experimental physicist. The way that I learn and think about things is in, let's say, broad concepts rather than equations on a paper. But I definitely have met some people who have said, unless you show me the equation, I cannot understand what's going on. And I just find that bizarre. But I guess it's different ways of thinking. I have one last question for you that I have been asking to everybody. Do you have a favorite science fact that you want to share with us?
I do, and this came from teaching sustainable energy. Okay. And I was so shocked by it, I went and checked it 3 times before I actually taught it to any classes. But the most amazing statistic I actually found is that if you take all the nuclear accidents that have happened from nuclear power stations, all the pollution that's come out of those is less than you get out of a 1 gigawatt coal-fired power station over 1 year.
Really?
And that was quite a shock. Now, it's a little bit disingenuous because some of the materials that have come out of Fukushima and out of Chernobyl and so on are far more dangerous to humans and to animal life and so on. But in terms of volume, it's a tiny volume compared to the amount of CO2 and the amount of sulfur dioxide and other pollutants that come out of coal-fired power stations.
That is really surprising. Yeah.
Well, it's fairly easy to do the back of the envelope calculation and get the numbers.
Mm-hmm.
The nuclear accidents, you need to get, people going around collecting radioactive particles and other fallout to understand the volumes. But, the amount of energy in nuclear fuel is enormous. E equals mc squared. It's completely enormous to what you have in fossil fuels. And it's that, almost a factor of 1 million higher energy density really means you have extremely small amounts of fuel, small amounts of pollution as well, and waste compared to what you get from any coal-fired power station or burning petrol or diesel or any other fossil fuel.
Yep, that is shocking, and I think a good point to end on. So thank you very much, Doug. It's been a really interesting conversation. Thank you.
Thanks very much for the interview.
You've reached the end of the podcast, which probably means that you enjoyed what you're listening to. So please don't forget to like, follow, subscribe, and share this podcast series as much as you can. The more you do those things, the better this podcast is going to be. Don't forget, you can always contact me by email at ash@crackingquantum.co.uk. And please join me again for another episode of Cracking Quantum.